The purpose of this lecture is to introduce P control on a real process, as well as teach you how to determine the sign, i.e. plus or minus, of the controller gain Kc. The sign of Kc is not subjective. There's a correct sign and there is an incorrect sign. And you choose the one that leads to corrective controller action. So to set this problem up, we have our familiar salt mixer, okay? And we want to maintain C at a set point, right? So that must be the controlled variable. So we want the salt water to be at a certain concentration. This is the controlled variable. The manipulated variable is the mass flow rate of salt W that's coming into the reactor, right? So this is your manipulated variable. And at this point, we can still set up a controller because it would be interesting to consider set point changes. But there's also a disturbance variable in the mix here, and that is Q. This is the disturbance variable. So the flow rate of pure water is highly variable and unpredictable. So this is the disturbance. Disturbance variable. And that is in the problem statement here. The disturbance variable is Q. An important thing to note is that the salt conveyor belt, and I'll use a different color for this, is direct acting, okay? And what that means is as this electronic signal that's output from the feedback controller is fed to the conveyor belt, as this input to the conveyor belt increases, the speed of the conveyor belt also increases. Okay? If it were reverse acting, if you jack up the electronic signal fed to the conveyor belt, the speed would decrease. That would be reverse acting, but it's direct acting. The salt concentration analyzer is direct acting as well. And what that means is that as C increases, the actual concentration in the tank, C tilde increases too. And this is the electronic signal output by the salt concentration analyzer and fed to the controller, okay? And then this internal to the controller gets converted into an internal set point in milliamp units. So as usual, the error is defined as the set point minus the measurement, okay? And the measurement is in milliamp form here. And under a P control law, the controller output, which is right here, this is the controller output. And since this is a P controller, this is equal to the P action. Okay? Okay, it's a function of time, and it's proportional to the error, okay? And this here is your controller gain. And this here is your offset, right? And when the error is 0, that's what the speed of the conveyor belt is to maintain, and this is what maintains the salt concentration at C set point at steady state conditions, okay? So just for fun, let's sketch out the block diagram of this. So at the very beginning, we have our set point, right? And this is actually converted into an internal set point via a gain Km, right? And I'll write the units below all of these, okay? And the error is defined as a set point minus the measured concentration, right? Okay, and this spits out the error here, okay? And right here is going to be the measured concentration, okay? And so far, these are in units milliamp, this is milliamp, this is milliamp, and this is grams per liter. All right, and that error is fed to your feedback controller, okay? And your feedback controller is a P controller, and it has gain Kc, okay? So this is your P controller. And the controller outputs a milliamp signal that is then fed to the conveyor belt, okay? So this is going to be a milliamp signal. and it outputs V tilde, and I use V for velocity, the velocity of the conveyor belt, okay? And then something inverts this velocity into an actual salt flow rate, okay? So we'll call this KB, and we'll assume that it's proportional. Not necessarily true. Okay, so this is a conveyor belt. And it results in a certain salt concentration W, okay, grams per second. And this is the conveyor belt. That's why I chose B. All right, and then W affects the process through a transfer function, which we've derived before. And that transfer function is 1 over Vs plus Q. We've derived this before. This is Q bar, okay? All right, and this is the contribution to the concentration. And these all need to be written in the frequency domain, so I'll make sure it's clear that that's capital, okay? So this is a capital C. I'll make this bigger. Capital C. And this should be capital V tilde, right? And we'll write them in deviation form as well. Okay, so this is the contribution to how salty it is by the salt, okay? But that's not the only contribution to how salty it is, right? There's another one, all right? The other contribution is from Q, right, the disturbance variable. And we've derived what that disturbance variable is, what its transfer function is, plus Q bar. We had to linearize it, so that's why I have these bars on here. And this is Q star, okay? So this is our disturbance, right? So we can highlight these. This is our disturbance. This is our controlled variable. This is our manipulated variable, right? And this is another input, the set point, okay? All right, and then this is, we have our salt concentration analyzer. It might have some dynamics, so we'll give it some dynamics. GS of S, okay? All right. And then this is your measured salt concentration, okay? So this is yours, this is the process. This is the process as well, just how it affects, or how the disturbance affects it. And this is your salt concentration analyzer, I'll say sensor for short, okay? And this has units of grams per liter. Q has units liters per second, right? So this is grams per liter as well. Grams per liter. Okay, so I think this process, this block diagram is complete here. Let me move this down. Yeah, this is complete, okay? And I guess I'll label these too. So here's our controlled variable. That's how salty it is. This is disturbance. All right, this is the manipulated variable. And so this is an input, right? Think of this as an input. And this is another input, right? So I'll just put this as an input. It's a set point change, another input. So there are two different inputs. And my claim is that this, so here's our controller. So I'll color this, all right? That's the heart process control, put a little heart there. And my claim is that while you may be able to choose how aggressive your controller is by the magnitude of Kc, it needs to have a certain sign in order to have corrective action. And here's the chain of logic that you use in order to determine what sign Kc has to be. And it's determined by the physics of the process, i.e. how Q affects C and how W affects C. And also the fact that the analyzer and the conveyor belt is direct acting. We need to know that too. So here's what I usually do. I usually consider a hypothetical scenario, okay? So let's say that C is less than CSP, okay? So what that means is the set point is greater than the salt concentration, and in words, it's not salty enough. Okay, and this could be caused by whatever. It could be caused by owing to a set point change, or a disturbance. It doesn't matter which one. The sign of Kc is irrelevant to what caused C to be less than the set point, okay? But all we know is that it's not salty enough. And now we have to think about what we want to happen, okay? So since it's not salty enough, we want W is our manipulated variable. So we think about what we want the manipulated variable to do. So we want the manipulated variable W to increase, right? And that's because the more salt we dump into the reactor, the higher the salt concentration will become, okay? And that's sort of apparent here. So I'll put a plus sign here. So this is a positive gain, right? So you can look at the gain and tell that as well. So even if I told you nothing about the physics of the process, you can tell by the gain here that you need W to increase in order to increase C. It's a positive gain here. All right, so you want the manipulated variable to increase, all right? However, in this scenario, okay, the error, E of T, okay, is set point minus the measurement, okay? And this is a millimp form, but it's direct acting, so C tilde is proportional to C, okay? Directly proportional. So the error in this scenario, if the set point is greater, is positive, right? So the error is positive, okay? And then P action is, so what we want is P action, which is V tilde, since this is direct acting, in terms of if V tilde increases, W will increase as well, right? So what we want is V tilde to increase, okay? And this is because sensor is direct acting. Is direct acting, okay? Oops. Okay, so let me move this down here. So there's one more piece, I should say. So because the conveyor belt is direct acting, because we want W to increase, we also want V tilde, which is the direct controller output, to increase. All right, finally, we can say the error is positive because of what we supposed, right? That's simply, if we say that, then that implies that the error is positive, okay? Just by our supposition. All right, and if we want V tilde to increase, V tilde equals Kc E of T. We want this to increase, right? We want that to be positive. Well, I should say it's proportional to that, okay? Because we have our V bar too. So if we want V tilde to increase, will increase if we choose Kc to be greater than 0, right? Because if we choose Kc less than 0, what's going to happen is we will decrease V tilde, okay? So that's the logic to know what sign of the controller gain should be. So if you don't have Kc greater than 0, then your controller will act in the inappropriate way, okay? And in fact, whenever it will actually exacerbate the situation. So if you're not salty enough, it will dilute it even more, okay? So I encourage you on your own to suppose that C is greater than C set point, okay? And then walk through this logic and you'll get the same answer, okay? Because this means that it's too salty, right? And you'll arrive at the same situation, okay? So I encourage you to do that on your own.